Hello, my people. Welcome back. At the end of the first video, we finished with talking about the definition of a radian. And I proposed a different way of thinking about the radian rather than the official definition. I find the official definition annoying, personally. But then, of course, I find a lot of things annoying. But think of it however you want. Because both of them actually get at what is being communicated. I just find that the sort of way of thinking about radians as a way of expressing the fraction of a full revolution just to be a little bit more not only meaningful to me, but also consistent with how we then turn around and use radians, and therefore easier to remember. But of course, if we're dealing with radians and degrees, just like if we're dealing with, meters and feet or kilometers and miles or Fahrenheit and Celsius, we have to figure out a way of converting one to the other, right? And that is exactly what these ratios do. To convert degrees to radians, we multiply by pi radians over 180 degrees. And if you're ever curious as to how you can tell, so to convert radians to degrees, multiply by, of course, its reciprocal, 180 degrees over pi radians. And if you're thinking to yourself, I never can remember which one to multiply. Well, which one's going to cancel out correctly in terms of the units that are being used? That's really the easiest way to do it, okay? So let's go ahead. And of course, these ratios are done because 2 pi is a full revolution, and 360 is a full revolution. So 2 pi over 360 reduces to pi over 180, and that's why we use these ratios. I stole a couple of example problems, and we'll use these as a way of just sort of running through a couple of examples before we move on to talking about, arc length and angular velocity and linear velocity and all sorts of fun stuff like that. Those sort of pre-trigonometry word problems that help us really kind of get our mind around what we're doing when we're dealing with these measurements that we then turn around and apply trigonometry to. Okay, first things first, we have 325 degrees. Okay, degrees. That means that I'm going to multiply by pi radians over 180 degrees, because degrees here and degrees there will cancel, right? Because 325 is basically 325 over 1. Now, if we have 325 and 180, we ought to be able to reduce that in our head, but I'm not going to deal with that right now. And we wind up getting, if we reduce it, we wind up getting 65 pi over 36, okay? And basically all that says is that the only common factor that those two had was a common factor of 5. So basically it was 325 pi over 180. They both had a common factor of 5. It reduced to 65 pi over 36. Now, if we move over to 60, we ought to recognize this one. So we ought to know the answer before we even get there. Okay, but let's go ahead and just grind it out in terms of our formula. And we have pi over 180. And we use that one again because we want the degrees, we want the units of degrees to cancel. And 60 degrees is understood to be 60 degrees over 1. When I multiply it by pi over 180, the degrees cancel out, and I'm left with pi over 3. Right? Alrighty, well, let's go ahead and go the other way. We have negative 4 pi over 3. Well, negative 4 pi over 3, we're going to multiply by 180 degrees over pi radians. And that's because I want the degrees to be the unit of my answer, and the radians, insofar as we can really think of them as a unit, are going to be the ones that cancel, okay? Now, obviously, the pi's cancel. Boom, boom, okay? 3 is going to cancel with the 3 that is inside the 180, and all I'm left with is negative 4 times 60. which is negative 240 degrees. And there's my answer. Okay, let's move on to one more. We have 23 pi over 12. Again, since we want our answer to be in degrees, that is going to be the unit that we put on top of our conversion ratio. We see the fact that pi and pi cancel out. 12 does go into 180. Now 180, of course, is 120 plus 60. 12 goes into 120 10 times. It goes into 60 5 times. So it winds up being 15, okay? And basically all we need to do is now multiply 23 by 15. Okay, now 20 by 15 is 300. 3 by 15 is 45, and therefore it is 345 degrees. Okay. And these ought to be really, really straightforward. And the reason why we practice these is because it really does drill into our head basically the relationship between these very, very familiar degree measurements that we know and these relatively new radian measures that we're getting to know. And in basically driving it into our brain, it is then pushing it from the short-term memory into the long-term memory, which, by the way, is the whole purpose of homework in general. Just kind of throwing that out there. If you're ever wondering why, if you ever wondered why you don't have a firm grasp of the material, despite the fact that you understood the lecture, if you didn't do the homework, you never engaged in the process by which that iterative sort of over and over again process that takes things from the short-term memory and drives them into the long-term memory. Now, I do want to take a look at this down here because every once in a while when you're dealing with a trigonometric problem, you're not being given degree measurements like this, okay? You're not being given degree measurements in terms of decimals, right? You're being given them in terms of degrees, minutes, and seconds, okay? And if you're thinking to yourself, what in the world does this have to do with time? Why are they calling them minutes and seconds? Minutes and seconds are measurements of time. Well, yes and no. Basically, we call them minutes because they are minute parts of the hour. And we call seconds seconds because they are secondary minute parts of an hour. So you can chop more than just hours up into minute and secondary minute parts, and that's what they've done with degrees. And it should not be a surprise to us that they do this also with degrees, because the idea that there are 60 minutes in an hour and there are 360 degrees in a circle, you should have noticed that relationship in terms of 360 being a multiple of 60, okay? So what we have here, and just for sake of room, I'm going to bring this down, okay? And I'm not going to do 7 and 10, largely because rarely, I mean, the only reason for you to convert a degree measurement in decimals back to minutes and seconds is just for the sake of doing so. And it's a little less straightforward, so we're just going to concentrate on how to interpret these anomalous ones when we find them. These are kind of old school, and in order to sort of plug it into our calculator, we need to be able to transform them into the decimals that they represent. I've already told you that they are minute parts, and like time measurement, those minute parts are out of 60. So 7 minutes, 7 minute parts of a degree is another way of saying 7/60ths of a degree. And then the next part is 57 secondary minute parts. 57 seconds is, of course, 60 squared degrees. Okay, that is not a zero exponent right there. That's the degree symbol. And basically from here, all you got to do is plug it into your calculator, right? Okay. Well, let's go ahead and do that. We have 232 plus 7 over 60 plus 57 over, and you can put 3600 or just 60 squared if you want. And that winds up being there. Of course, and if you get the decimal right here, you need to change it from decimal into, from fraction into decimal, and it winds up being 232.133, and of course that's an approximation degrees. I need you, and this is just sort of, and you'll hear me say this about a dozen more times before we start in the fall. I need you to get into the habit of when you approximate, you always, always, always approximate to 3 decimal places. I need you to get into that habit because on a P exam for calculus, those are the instructions. And if you're already in the habit of doing it, for me, for an entire year, then it is not going to be, it's not going to be a chore to remember to do so when it comes time for the AP test next May, okay? And of course you would do the same thing with this number 9 right here, okay? You would basically say, well, that's negative 154 degrees, and then you need to take 47 minute parts and 42 secondary minute parts. And, like I said, you can do it as 3600 in the denominator or 60 squared. It doesn't really matter to me because, of course, they mean the same thing. And let's go ahead, and that's 154. And I'm just going to do it as the positive. I'll include the negative in the final answer. Okay, and boom. And what we get there, and of course that's annoying, but we'll just go ahead and do it that way. And that actually, and because it's actually goes to 3 decimal places, that's actually not an approximation. So we will not do our squiggly equal sign. That actually is the correct answer to 3 decimal places. And those are kind of the conversions that we need to be familiar with. And we do these sort of Mickey Mouse kind of questions because they just ensure that we have those things down really, really well before we move on and apply this knowledge to things that are, of course, a little bit more difficult. And by more difficult, and this is not terribly so, we're going to talk about arc length here for a moment, okay? And I basically stole some of these. I basically stole all of these things, and I tried to give you the source if they were sort of, famous copyrighted materials. Ron Larson, this is actually, when I taught pre-cal the last time, I actually taught out of Larson's book. I love Larson's book. We will be, it's funny because Ron Larson and James Stewart both write a pre-cal book and a calculus book. I prefer Larson's pre-cal book. Y'all learned pre-cal out of the Stewart book. But our calculus textbook will be Stewart's calculus textbook. I love his calculus textbook, and it'll serve us well in the coming year. Now, we've already touched on this a little bit when we were talking about the definition of radians, or my quote-unquote better way of thinking about radians, because we talked about how circumference was merely one special case of arc length, okay? And notice here that the way that they have defined arc length, for a circle of radius r, a central angle theta intercepts an arc of length s given by s is equal to r theta. So basically the arc length, so s is basically standing in for arc length. And it's standing in for arc length, and it's not a c because we are looking for any arc length, not a particular arc length. If we were looking for a particular arc length, being the circumference, we wouldn't have theta right here. We would have 2 pi. We would have a specific theta. But seeing as we are dealing with basically a formula to allow us to arrive at any arc length, we have to get rid of the 2 pi and instead put in theta. So where theta is measured in radians. And you'll see from these examples here in just a moment why I talk about radian as not really a unit of measure, okay, in the standard sense of the word, because you're going to see radians here just sort of evaporate. It says, note that if r is equal to 1, meaning if it's the unit circle, then s, being your arc length, is equal to theta. And the radian measurement of theta equals the arc length, okay? Now, all of that, blah, 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 and you're like, okay, that's really great. Why don't you show me how this actually works out? Okay, let's go ahead and take a look at these practice problems right here. It says the minute hand of a clock is 8 inches long, and it moves from 12 to 2 o'clock. How far does the tip of the minute hand move? Express your answer in terms of pi and then round to 2 decimal places. Okay, we are going to ignore the 2 decimal places, and we might not even round. Let's just sort of ignore the and then round, because oftentimes I don't want you to approximate if there is a way, or at least a relatively simple way, of expressing the exact value. I only want you to approximate if it's necessary, okay? And you'll learn over time kind of what I mean by that. But basically we have a clock, right? And I've only basically done one circle right here. So let's talk about just the circle that is swept out by the tip of the minute hand, okay? If the tip of the minute hand is at 12, and then it goes, and here is 3, and here's 1 and 2. If it goes to 2, right, then it has swept out 2/12 of a revolution, or 1/6. 1/6 of a revolution, if a full revolution is 2 pi, corresponds to the radian measurement of pi over 3. Okay. So basically, that means our theta is pi over 3. And if you want, you can say radians, okay? Now, remember, our formula is arc length is equal to radius times theta. In this particular case, you already know the radius. It told you that the minute hand was 8 inches long, right? There is your radius. And so you have 8 inches, and then you need to multiply that by your theta, pi over 3 radians, okay? And what happens here is you get 8 pi over 3 inches. Because it says how far did the tip of the minute hand move. Now, usually when you multiply 2 units by each other, like in physics, you get a foot-pound, right? When you multiply feet by pounds. Here, you don't get inch radians or radian inches. You just get inches, right? And that's what I mean by radians kind of being almost like a pseudo-unit. They merely express in a particular way the fraction of a full revolution that you are actually talking about in terms of angle measurement. But when you multiply it, it just evaporates. It goes away, and we're not used to seeing that in true units, and that's why I kind of wanted to give you a heads up, because those of you who are going to be really, really meticulous, if I hadn't given you a heads up, you might have really, really gotten frustrated and wondered where the heck it went. Well, it didn't really go anywhere because it was never really there to begin with. And that's kind of what I'm trying to drive home right there. Okay? Let's go ahead and do one more, and then we'll sort of call this one to a close, and we will have a third video sort of finishing up. The radius of a wheel rolling on the ground is 80 centimeters. Okay, that's a big wheel. If the wheel rotates through an angle of 60 degrees, how many centimeters does it move? Okay. Well, here's the thing. This is basically a really similar problem to this. I wish it hadn't been the same angle measurement. Let's actually change that. Okay. Let's say that it's 135 degrees. Okay. Let's change it just so it isn't pi over 3 again. But instead of the minute hand moving, right, it's the whole wheel is rolling. So basically, the point that is down. So, if this point is down right here and it rolls 135 degrees, we're looking for the wheel where that point is now up there, right? Because every bit of this arc length, and actually it should have been, it should have been up there, because if it rolls like this, then it'll spin around like that. But basically what we need is, if this is the new point that touches the ground, then basically we need to calculate this arc length, because every unit of length along this arc length basically will correspond to one. It will correspond 1-to-1 for the ground measurement that it covers. We're just sort of assuming it doesn't slip at all, right? So if you have a wheel that is exactly 2 meters in circumference and you roll it once, it will be exactly 2 meters away from its original position, as long as we assume that there isn't any slippage in terms of when it was rolling. And so what we need now is we need this arc length, because this arc length basically maps onto this length right here, okay? And if you can hopefully you can sort of imagine that. And if you can't, just think about it this way. If it's basically rolling out like that, okay? So basically it kind of rolls like this, and we get that. Okay, that's enough. If you don't get it, then we can talk about it at another time. Now we know that 80 centimeters is its radius. Okay, it wasn't even coy about the way that it described it. Right here, the minute hand of the clock is 8 inches, and it didn't call it the radius. You had to recognize it as the radius. Here, that's the radius. Okay. Now 135 degrees needs to be converted into radians. Now radians, 135 degrees, it becomes 3 pi over 4. So our arc length is going to be r theta, and r is 80 centimeters, and then theta is 3 pi over 4 radians. And remember, radians are kind of a pseudo unit, so when you multiply this out, you're not going to get some quantity that is radian centimeters or centimeter radians. You're just going to get centimeters, okay? Because length is length is length, right? Now when I multiply these out, I notice that 80 is going to wind up in the numerator with the 3 pi. Well, 80 cancels with the 4 and leaves 20, and so basically this winds up being 60 pi centimeters. Okay? And that's basically, arc length really isn't all that difficult, and I understand sometimes we sort of cower away from word problems, but you're going to be doing a lot of them in the next year, so we'll practice them over and over and over and over and over again, and hopefully, just like anything else, it's merely time and exposure that takes the scariness of anything away and leads us to mastery. So. In the next video, I will do one more problem of arc length, and we will discuss briefly angular speed and linear speed, which are basically sort of just cousin concepts of this one. But yeah, look for that. And if you have any questions on any of these videos that are posted, please do shoot me a message in Teams. citing which video it came from. I will also, when I do videos like this, I will be posting these sheets right here, a scan of these sheets along with the link to the playlist that I create and post within Teams. Y'all will sort of get the feel of it, of how I post things and stuff like that. But I will always, if possible, post the work that I've done, the pages that I've done in those videos along with the link to the playlist. Okay? Bye, guys.